Imagine trying to precisely measure a single drop of water, right? But instead of behaving like a liquid, the water acts like a giant bouncing sponge.
Which is just a totally frustrating concept to even picture.
Oh, exactly.
Yeah.
Because every time you try to push it, it squishes backward before it actually moves forward.
Right.
And now, imagine your job depends on putting exactly the same microscopic amount of that bouncing sponge into a mold, like thousands of times an hour.
Yeah. And that is the frustrating reality of modern manufacturing today.
It really is. You look around and the physical world is just shrinking.
Yeah.
I mean, if you were listening to this on a pair of high-end wireless earbuds, the tiny components inside them were likely injected in the literal blink of an eye.
Oh, absolutely. Milliseconds.
Yeah, the medical microfluidic chips in healthcare, the tiny sensors packed into your car's bumper, the microscopic fiber optic connectors keeping your internet running, everything is getting smaller.
And the demand for these ultra-precision microparts is absolutely exploding.
Right. But the secret that the manufacturing world is currently wrestling with is that the traditional way we make these plastic parts, well, it's hit a literal physical wall.
We truly are bumping up against the rigid laws of physics here. I mean, conventional manufacturing methods simply cannot scale down endlessly.
And that is the mission for our deep dive today. We're exploring a groundbreaking 2025 white paper from MHS, which is a Westphal Technic company, detailing something called the ISOKOR process and M3 technology.
It's fascinating stuff.
It is, but I have to be completely honest here. As someone who has spent years as a traditional plastics engineer on the factory floor, tweaking screw recovery times, managing melt cushions, and relying on heavy machinery to push molten plastic well, when I first read this paper, I was highly skeptical.
I don't blame you at all. It's a huge shift.
Right. I'm used to doing things the conventional way. But as a specialist in this M3 technology, you are here to tell me that my old assumptions are essentially obsolete.
Yeah, when we were talking about the true microscale, so parts weighing a fraction of a gram, obsolete is definitely the correct word.
Wow, okay.
Your conventional screw and plunger injection molding machines were designed for macroscopic parts. They were fundamentally not built to do what modern technology is demanding of them.
Okay, let's unpack this, because before we get into the shiny new M3 tech, I need you to explain the mechanics of why my tried and true methods are failing.
Sure.
Let's say I'm trying to mold a tiny gear for a medical device that weighs between 1 and 1,000 milligrams. Why is my standard injection molding machine suddenly useless?
Well, the failure really comes down to volumetric metering.
Okay.
In a conventional injection molding process, the machine is designed to push a very specific physical volume of melted plastic forward into the mold cavity. You're measuring a linear distance, basically a physical stroke of the screw or the plunger.
Right, which is how we've always done it.
Exactly. And for a coffee cup or a car dashboard, measuring volume by distance works beautifully. But when your part is 1 milligram, the volume required is microscopic.
Right.
And here's the fatal flaw. Thermoplastic melt is not a perfect, incompressible liquid like water. It is highly compressible.
Okay, let me make sure I'm picturing this correctly. The plastic melt expands and contracts wildly with changes in temperature and pressure.
That is the core issue, yes.
Yeah.
Now, factor in the geometry of a high-cavity mold. You have the melt metering cushion, which is the reservoir of plastic waiting to be injected, plus the entire volume of melt sitting in the hot runner distribution channels.
Right, the whole delivery system.
Exactly. In a conventional process, as your machine pushes forward to inject, all of that waiting material compresses before it ever starts flowing. That runner system acts as a buffer.
Oh, wow.
Yeah, it absorbs up to 15% of your injection metering stroke, just in pure compression.
Wait, so my machine thinks it has injected a perfect, tiny, full shot into the mold because the screw moved the correct distance, but the plastic is actually just absorbing the force like a giant sponge in the runner system.
You nailed it. That's exactly what's happening.
No wonder traditional engineers see such inconsistent density and poor cavity replication at that scale. The machine is literally lying to us.
The machine is giving you a macroscopic measurement for a microscopic reality. The sponge effect completely destabilizes the process.
Man, that is frustrating.
It gets worse, because the mechanics of conventional molding build pressure from zero every single cycle.
Right, it resets.
Yeah, it drops to atmospheric pressure, the screw pushes, the plastic compresses like a sponge, the pressure slowly ramps up, and finally the melt begins creeping into the cavity. But that ramp-up takes crucial time.
And when you are molding a part the size of a grain of sand, time is a luxury we definitely don't have.
You have mere milliseconds.
Eh.
Because the micropart is so incredibly tiny, It has virtually no thermal mass to retain its heat.
It cools off instantly.
Exactly. If your injection is slow because you're busy building pressure from zero, the plastic hesitates as it hits the cold steel of the mold. It begins to freeze instantly.
Ugh, the worst.
Yeah, you end up with weld lines, frozen surface layers, and poor structural integrity before the cavity is even halfway full.
This raises an important question then, because if volumetric metering trying to push a specific volume of plastic is completely dead at the microscale, what do we replace it with?
Right.
I mean, we can't simply change the laws of physics. The plastic will always have compressibility.
We can't change physics, no.
My traditional engineer instinct says we need to build an impossibly stiff machine to overpower the sponge. But you're telling me we shouldn't fight the compression at all?
Attempting to overpower it is a losing battle.
Hmm.
To solve the sponge problem, we have to stop fighting the compression and start actively harnessing it.
Harnessing it. Okay.
Yeah, and this brings us to a fundamental shift in polymer physics, specifically a concept known as free volume.
Free volume. Okay, take me back to Polymer Chemistry 101. Are we talking about the space between the actual molecular chains?
Precisely. Imagine the macromolecules of the plastic like a massive bowl of cooked spaghetti.
Okay, I'm with you.
At standard atmospheric pressure, even when the plastic is fully melted, there is empty, unoccupied space between those entangled, squirming molecular chains. That empty space is the free volume.
Got it.
When you heat a polymer up to its molten processing temperature, its overall volume expands. The molecules vibrate and move around more aggressively, pushing away from each other and creating even more free volume.
That makes intuitive sense. Thermal expansion basically creates more empty space at the microscopic level.
Exactly. Now, if we take that fully expanded, non-pressurized melt and put it into a completely closed steel system, and then we apply immense pressure, we can force those spaghetti strands closer together.
Or crushing them.
We physically crush the free volume out of existence. According to the data in the MHS white paper, amorphous polymers like polycarbonate can be compressed by 5 to 10% in volume.
Wow, that's significant.
And semi-crystalline polymers like polypropylene, which have more organized molecular structures, they can be compressed by 10 to 15%.
So instead of acting like an incompressible liquid being shoved through a syringe, the plastic melt is behaving more like a heavy-duty coiled spring.
A coiled spring is the perfect way to look at it.
By squishing the molecules into that empty free volume, we are literally charging them up with potential energy.
That is the massive paradigm shift of the M3 technology right there. We are entirely abandoning traditional volume-based metering, where the machine pushes a physical volume and moving to energy-based expansion molding.
Okay.
We pre-compress the melt, store that compression as elastic energy, and then use that stored energy to explosively expand the melt into the microcavity.
That is a wild concept to wrap my head around, but from a strict engineering standpoint, how do you actually measure and control an invisible coiled spring of liquid plastic?
It sounds impossible, right?
Yeah. If I can't rely on the physical stroke distance of my screw anymore, how do I calculate the exact amount of energy I'm putting into my spring? If I overpressurize it, the expansion could blast the mold apart, and if I underpressurize it, I get a short shot where the part doesn't fill.
You calculate it using the material's PVT diagram. That stands for pressure, volume, and temperature.
Okay, the PVT diagram.
Think of the PVT diagram as a highly detailed topographic map for polymer behavior. Every single thermoplastic has a unique PVT fingerprint that dictates exactly how it behaves under varying conditions.
Wait, so you're using this diagram like a map to calculate the exact amount of mechanical force needed based on the temperature?
Yes, exactly.
Yeah.
The M3 process uses this map systematically. By looking at the exact intersection of the material's transition temperature, the point where it shifts from a solid to a melt and its actual processing temperature, you can calculate the precise percentage of volumetric compression required to fill a specific microscopic void. You enclose the melt, apply a highly controlled specific force, and the PVT data tells you exactly how much elastic energy you have just stored in your system.
Here's where it gets really interesting. Because the textbook physics of free volume and elastic energy, they make perfect sense on paper.
Sure.
But as an engineer, I need to know how we translate this beautiful theory into cold, hard steel. If my traditional reciprocating screw is useless, how do you actually build a machine that can hold a coiled spring of liquid plastic without it exploding out the back? Are you just replacing the screw with a tiny, hyper-fast plunger?
Well, no, it's much more sophisticated than a simple fast plunger. The machinery that executes this is called the Melt Delivery Unit, or the MDU, utilizing the patented ISOKOR process.
The ISOKOR process.
Got it. It is a beautifully orchestrated three-step sequence designed to manage that energy. Step 1 actually happens back at a specialized screw, but unlike your conventional machine, this screw isn't reciprocating.
It's not plunging forward.
No, it's not moving violently back and forth to inject. It functions simply to apply a constant, continuous pre-compression to the melt cushion. It establishes our elevated baseline pressure.
So the entire system is already pressurized. The spring is slightly coiled before the cycle even begins.
Correct. Then the melt moves into the MDU manifold. Here is step 2. A dedicated plunger piston moves forward. This plunger compresses the melt further, pushing it to a very specific, mathematically calculated pressure plateau.
Using that PVT map.
Exactly. And because it's rapidly squishing the molecules together, we actually get an adiabatic temperature rise.
Okay, let's break that down for the listener. Adiabatic temperature rise. Is that like when you use a manual bicycle pump to fill a tire and the bottom of the pump gets physically hot in your hands just from the friction of the air being compressed?
That is the perfect analogy. The mechanical friction of the molecules being forced together generates a tiny, highly predictable amount of internal heat. At this exact moment of peak compression, the check valves behind the melt are closed, the valve gates at the mold are closed, and the entire MDU is functioning as a highly pressurized, closed-system vessel.
We have locked the fully compressed spring in a steel box, just waiting for a release valve.
Which brings us to step 3. The valve gate at the mold suddenly opens. Because the pressure in the empty microscopic cavity is basically zero, the highly compressed melt instantly expands into the void to equalize the pressure.
Oh, man.
We aren't actively pushing it with a stroke. The stored energy is causing it to practically explode into the mold in a matter of milliseconds.
Milliseconds, that is fast.
And crucially, while this explosive expansion is happening, that MDU plunger is simultaneously inching forward just enough to instantly reestablish the pressure drop. It maintains that high plateau. Finally, the valve pin slams shut.
Okay, I have to throw a flag here as a skeptic. Didn't the plastics industry already try this concept decades ago? I remember a technology called expansion injection molding, or EIM. Isn't ISOKOR just older EIM technology rebranded with a fancy new acronym?
It is a totally valid pushback, but they are fundamentally different in their mechanical execution. Traditional EIM does use melt expansion, yes.
Right.
But in EIM, the machine still builds that pressure from zero for every single cycle. The pressure drops to zero, ramps up to a massive violent peak, expands into the mold, and drops all the way to zero again.
That sounds exhausting for the machine.
And the plastic.
Mm.
Imagine taking a metal slinky and violently stretching it as far as it goes, then crushing it flat over and over again. You mechanically stress and damage the polymer chains.
Ah, so EIM pulses the pressure, which fatigues the plastic.
Precisely. ISOKOR is radically different because of that step 1 I mentioned, constant pre-compression. The pressure in the MDU never, ever drops to zero.
Oh, I see.
We are starting the cycle from a higher baseline melt density, stepping it up to a plateau, and ending with a higher melt density in the cavity. Because the molecules aren't being subjected to massive violent pressure swings, the final micropart has significantly less internal stress, far less warpage, and vastly superior cavity replication.
That solves the pressure pulsing problem beautifully. But listen, any traditional plastics engineer listening to this just had their blood pressure spike for a totally different, terrifying reason.
Oh, I know exactly what you're going to say. You're thinking about the residence time of the plastic.
Yes, melt residence time. You just described taking highly sensitive thermoplastic, holding it at its maximum processing temperature, and keeping it constantly under extreme pressure in a giant hot runner manifold acting as a pressurized reservoir to make parts that weigh maybe 5 milligrams.
It sounds like a recipe for disaster.
Right. At that consumption rate, it could take hours for a single pellet of plastic to actually make it out of the nozzle. Under that much heat for that long, the molecule should degrade, turn brown, break their bonds, and turn into useless soup.
And if you try that in a conventional, non-pressurized system, they absolutely would turn to soup. But this is where the physics of the ISOKOR process get incredibly counterintuitive.
Yeah.
What actually causes melt degradation?
Well, heat.
We assume it is just heat. But heat is merely the catalyst. The actual mechanism of destruction is Brownian molecular motion.
Brownian motion. Okay, the random, erratic, chaotic oscillating of particles suspended in a fluid.
Exactly. When you heat up a polymer, the molecules vibrate and oscillate wildly. If they have the space to move around that free volume we discussed earlier, that erratic, violent motion eventually overcomes the chemical bonds.
They break apart.
The polymer chains literally shake themselves apart. They fracture. That fracturing is what degradation is.
Okay, that makes sense.
What's fascinating here is, because the MDU acts as a pressurized vessel that never drops to zero pressure, we are severely restricting that free volume.
Wait, really?
Yes, we are literally squishing the molecules so tightly together that they physically do not have the empty space required to vibrate and oscillate erratically. The constant extreme pressure mechanically suppresses the Brownian molecular motion.
Oh, so by keeping it under extreme constant pressure, you are actually putting a microscopic straitjacket on the molecules so they can't vibrate themselves to death.
The straitjacket is a perfect visual. The pressure protects the chemical integrity of the material. According to the MHS data, this constant pressure environment actually extends the allowable melt residence time by a factor of 5.
5 times as long. That's insane.
Right. Material that would normally degrade and turn brittle in 10 minutes can safely sit in the highly pressurized MDU for nearly an hour without losing any of its mechanical properties.
That completely flips traditional processing logic on its head. Most engineers are taught that pressure plus heat equals faster degradation.
Exactly. But the data proves otherwise.
And I imagine that molecular protection is especially vital when you start working with the really crazy high-tech plastics. I know the white paper heavily focuses on low-enthalpy supermaterials like PEEK and LCP, liquid crystal polymer.
Yeah, LCP is arguably the perfect case study for why M3 technology is necessary. LCP is an absolute supermaterial used in high-end electronics. It processes at an incredibly hot 340 degrees Celsius. And it has a very unique molecular structure, rigid, rod-like macromolecules that actually align themselves into structured liquid crystals when they flow. But it is a low enthalpy material, meaning it contains very little internal heat energy.
For the listener, let's contextualize enthalpy real quick. If a standard plastic with high enthalpy is like a heavy bowling ball,
Yeah.
it takes a lot of energy to get it moving, and it takes a long time for it to slow down and cool off.
Right.
But a low enthalpy material like LCP is more like a ping pong ball. It changes states instantly.
A brilliant comparison.
Yeah.
Because LCP is the ping pong ball, it freezes almost the exact microsecond. It touches the cold steel of the mold.
So fast.
If you try to push LCP slowly with a standard volumetric screw, it will just freeze solid in the gate before the cavity is even 10% full, and you get a rejected part.
So the M3 system uses the stored energy to outrun the freezing process.
Precisely. To mold a micropart in LCP, the ISOKOR process uses a valve gate open time of just 50 milliseconds.
50 milliseconds.
The compressed elastic energy allows the melt to hit explosive velocities of over 10,000 millimeters per second through a microscopic 0.5 millimeter gate. It's roughly 10 times faster than the maximum injection speeds of conventional machines.
10,000 millimeters per second. That's essentially a gunshot of liquid plastic. But wait, if the plastic is moving that violently fast, what about shear rates?
That's a great question.
Because high speed means high friction, and high friction means extreme shear. Doesn't that aggressive shearing rip apart those delicate, rigid, rod-like liquid crystal structures we just spent all this time protecting with our pressure straitjacket?
It would absolutely destroy them if the shear wasn't carefully managed across the entire journey. But the MDU is brilliantly designed to stage the shear rates.
How so?
Well, back in the barrel in the main manifold, where the plastic spends most of its time waiting, the flow channels are relatively wide and the movement is slow. The shear is kept deliberately low to protect the long molecular chains.
So we're keeping the straitjacket on, but moving them gently through the waiting room.
Right. But as the melt reaches the final nozzle, the geometry radically changes. The nozzle has an annular flow design, meaning the plastic is forced to flow through a tight ring shape.
Okay.
When you combine that tight geometry with the explosive expansion pressure, it subjects the melt to an incredibly high shear rate for just a tiny fraction of a millisecond. In polymer physics, this induces shear thinning.
Right, shear thinning.
The high friction forces the molecules to align perfectly, drastically dropping the viscosity.
The shear thinning effect makes it suddenly become as thin and runny as water right as it hits the gate.
Exactly. So it explodes into the cavity at maximum speed with minimum viscosity, effortlessly filling the microscopic features before a frozen skin layer can even begin to form on the cavity walls.
Right.
And then remember that final step? The valve pin violently slams shut.
Right, it slams shut. And you mentioned earlier that this forces one final peak of pressure into the cavity, packing the part. But why does that matter if the part is already full?
Because that final peak pressure does something almost magical to the thermodynamics. It shifts the transition temperature of the plastic.
Walk me through the WHY on that. Why does high pressure change the temperature at which a liquid becomes a solid?
Think back to the free volume. For a polymer to remain in a liquid molten state, the molecules need space to move around.
Okay, the empty space.
When that valve pin slams shut and spikes the pressure inside the cavity, it instantly crushes whatever free volume is left. It violently denies the molecules the space they need to be a liquid.
Oh, wow.
Because they are squished so tightly, they are mechanically forced into a solid state, even though the temperature is still technically high enough for them to be a melt. The extreme pressure forces the plastic to solidify instantly and uniformly.
So what does this all mean? We protect the plastic in a pressurized straitjacket. We drop its viscosity to water at the exact last millisecond. We explode it into the tiny cavity using stored energy, and we use a final pressure spike to force it to freeze instantly.
It means we get an absolutely perfect micropart. Because the cavity filled so fast and froze so uniformly, you get an isotropic inner structure.
So even stress everywhere.
Yes, the mechanical stress is distributed perfectly evenly throughout the part. You completely eliminate the warpage, the weak spots, or the microscopic density gradients that plague conventional volumetric molding.
And beyond just making a perfect part, from a factory floor standpoint, there is a massive economic and environmental victory here. Because the melt is protected from degradation in the manifold, and the valve gate can be positioned right at the cavity, it allows for direct gating on microparts.
Which is an absolute holy grail for micromolding.
It really is. I mean, in my old conventional setups, if I needed to make a 10 milligram medical gear, I couldn't inject straight into the part. I had to mold a cold runner system, basically a big plastic sprue with branching channels just to carry the plastic from the machine nozzle into the tiny cavity.
And that wastes so much material.
Tons of it. The runner would weigh a full gram, and the usable part would weigh 10 milligrams. We were literally throwing away, or at best regrinding, 99% of the premium, expensive medical-grade plastic every single cycle. This ISOKOR process completely eliminates the cold runner waste. You only use exactly the plastic that the micropart requires.
If we connect this to the bigger picture, mastering this kind of material density control and eliminating that scale of waste at the micro level is exactly what is going to unlock the next generation of high-performance technology.
We really need it to.
We cannot build the microscopic medical devices, the aerospace sensors, or the next-gen wearables of tomorrow using the clumsy volume-pushing machinery of yesterday. We had to stop fighting the natural compressibility of the plastic and start orchestrating it.
Shifting our mindset from pushing a liquid to orchestrating the release of a coiled spring. It's really brilliant engineering.
It absolutely is.
For you listening, whether you are wearing a smartwatch packed with microscopic sensors to track your heart rate or relying on fiber optics for your livelihood, the reliability of your world is quite literally depending on these invisible shifts in manufacturing. We rarely think about the physical machinery making our digital lives possible.
It is the hidden microscopic architecture of modern life.
It really is. And I want to leave you with a final, provocative thought to ponder. We spent a lot of time today talking about how holding plastic melt under constant extreme pressure inside the MDU suppresses Brownian molecular motion.
The pressure straitjacket.
Exactly. Effectively putting a straitjacket on the molecules to prevent them from shaking themselves apart and degrading under high heat. Well, think about the massive global challenge we have with plastics recycling right now.
Oh, that's an interesting angle.
Right. Because every time we melt down conventional plastic to recycle it into something new, the heat permanently breaks the molecular bonds, degrading the quality. This is why a recycled clear water bottle can rarely become another clear water bottle. It usually gets downcycled into a park bench or carpet.
Because of that thermal degradation.
Exactly. What if this exact same thermodynamic principle, using constant high-pressure closed system vessels to mechanically suppress molecular degradation during the melting phase, could be applied to mass-scale recycling? Could we theoretically melt and remelt plastics indefinitely, holding them in a high-pressure straitjacket without their polymer chains ever breaking down?
That is a fascinating application of the physics.
It is something to think about the next time you hold a tiny plastic sensor or toss a bottle in the bin. The bouncing sponge has become a finely tuned spring. Thank you for joining us on this deep dive, and keep questioning the process.